Section 16.2 Line integral. Last time we defined something called a potential field, and we said we will study when a given field can be identified as a potential field. To prepare for that, we will introduce something called a line integral. There are two types of line integral. First one is a scalar line integral, which means it's defined for a scalar function. So for a given curve, either in plane or space, let's say we start from a point and at another point, let's call this curve C, then the integration over this curve of a given function, let's say xy in 2D or xyz in 3D. So how do we define that? Well, this ds is known as a square root of dx squared plus dy squared in the Pythagorean theorem, or dx squared plus dy squared plus dz squared in 3D. But to integrate that, we have to parameterize this curve. So let's say this curve is parameterized as x equals x of t, y equals y of t, and z equals z of t. So t is a parameter. So we can write on the line integral as, line integral in this way, f. Let's use x and y, okay, to make it easier. This is x of t, y of t, and then this square root, it has x prime and y prime, right? Dx and dy. We can divide by dt, and inside it becomes dx over dt, or x prime t, and y prime of t, like that. So that's how you integrate. And of course, you have to specify the range of t. And in the special case that if y is given as a function of x, then the integral is particularly simple, because this is just y, and that's a function of x, and then since the parameter is x itself, so this is just 1, and this is y prime x, and the integration is over x. Okay, so in the special case that the parameter is x, this is the simpler formula, otherwise it's a more generic formula. And if it's 3D, then you just add z in the square root. Alright, let's see some examples. Suppose you are given a semicircle, x squared plus y squared equals 1, and let's consider the top half, so y equals non-negative number. Let's find out of course we know the length of this, right? It's just pi. Let's find out the integral of this function, x 2 plus x square y integrate over this curve. Okay, so we need to parameterize this. Well, there's a very simple parameter, just theta, right? And theta goes from 0 to pi. And the integrand is, well, what is x? Remember, this x, y is on the circle of a unit circle. So this x is just cosine theta squared. So x is cosine theta, y is sine theta, and ds is just the length, right? Which is just d theta. Okay, and that's very simple. So the integral is 2 theta plus, and you can merge this with that. So you get a d of negative cosine theta. Right, then you just use substitution. You get a cosine theta over 3, but there are negative signs, so it's negative, and plug in 0 in the pi. Right, and if you plug in pi, you will see this first term will give you 2 pi, and second term if you plug in pi here, you will see cosine pi is -1, so -1 cubed is still -1. -1 divided by that is 1/3. Then plugging 0, you get -1/3, so times 2, so it becomes 2/3. All right, so it's 2 pi plus 2/3. Okay. All right, so that's what you have. And let's see another example. Suppose you have a frame, a wire of semicircle, and this is just the axis, x equal other y equals 0. And let's find out the centroid of this frame. Okay, this is made of wire, so there's no interior. So it's not a disk, and not a half disk. So how do we find out centroid? Well, we need to find out the x dm, and in this case dm is just ds because the density is assumed to be 1 over the entire arc length, and this will give you x bar. But by symmetry, we know the center mass should be somewhere here. Right? So this must be 0. Let's find out y bar. So you have to integrate y ds divided by ds. Well, this denominator is particularly easy because it's just a total length. And the total length is the length of the semicircle plus the length of the diameter, which is pi over 2. Oh, sorry, pi plus 2. Now let's compute the numerator. Well, because the frame, the wire has 2 parts. This is 1, this is 2. Right? So we have to integrate by dividing into 2 parts. So this one equals, let's say, the C1 plus C2. And C1 is a circle, so let's parameterize by theta. And what is y? Y equals sine theta, and integrate from 0 to pi. How about second one? Well, second is particularly easy because y happens to be 0. Right? So the second one is just 0. Although if you parameterize this, you have to say ds equals dx. Right? And x goes from -1 to 1. But it doesn't matter, it's 0. So the integral is negative cosine theta 0 to pi, and that's 2. So where is the center mass? Y bar equals 2 over pi plus 2. And x bar equals 0. So that's the center mass. Alright, so you can see if the curve is not given by one equation, then you have to divide this into different curves and integrate one by one. Okay. Let's see one more example. Suppose you have a parabola y equals x squared. And let's say from origin to a point, and say this point is root 2, 2. Okay, x equals root 2, y equals 2. Let's find out the integral along this curve of, let's say, x times ds. Alright, what is that? Well, since this curve is given as y the function of x, so we can just use x as our parameter. So you have a square root of 1 plus that square, and what is this? This is the derivative of y over x, so it's 2x, and x goes from 0 to root 2. Alright, so let's try it. Aha, so we can just do the u substitution, right? And then this is square root of u, and the du equals 8 x dx. So this is du over 8, and the u goes from 1 to 1 plus 4 times 2, which is 9. Right, so you have a 1/8, then u to the 3/2 times 2/3 from 1 to 9. And that is, you can do the cancellation, you have 1 over 12, and then 9 to the 3/2 is 27 minus 1, and that is 26, which is 13 over 6. Alright, so that's our answer. Okay. Now let me give you another small challenge. If you have the same curve, but I want to integrate x times y, then you have this. Then how do you do it? Well, the same thing, x, y, and this is 1 plus 4x squared dx from 0 to root 2, right? But you have one problem. You have y there. How do you integrate that? Well, don't forget this y is not an independent variable. Y is on the curve, so that's nothing but x squared. So you will have actually x cubed 1 plus 4x squared dx. And then you can just finish it using the same u substitution, but the result is more complicated because of the cube here. Alright, I leave this as an exercise. So let's move on to the next topic. Vector integral along a curve. So suppose you have a curve, and this time we have to specify the direction. Last time we don't really matter. It doesn't really matter whether you are going this way or that way, but this time it matters. Say this is the starting point and end point. Then this integration over this curve of a vector field along this curve is not, this is not ds. This is a dr as a vector. So this is a dot product, and f is a vector. So you see vector dot vector, that's give you a scalar in the end, but how do we integrate that? Well, once again, you have to parameterize the curve, right? Let's say you have a x equals xt, y equals yt. Then this will be, let's say this is pq dot dx dy. Then that would be p dx plus q dy. Okay, that's a generic form, but how do you integrate? You have to change it to p times xt plus q times y prime of t, and then integrate over t, over your parameter. Okay, and in the special case that t is just if t is just x, then x prime of t, of course, is just 1, and y prime of t is just the derivative of y over x. Okay. Now, the vector integral along a curve and the backward curve, C1 and C2. they will be different. And this one, they're along the same path, but it's the opposite direction. It turned out that they are different. Actually, it is the opposite. Why? Because capital F is the same, but when you move along the segment, I mean this curve, each segment has a direction, right? And this dr and that dr as vector, they are not the same. They are opposite of each other. That's why the integral will be opposite of each other. All right? So that's something very different from the scalar integral. This is a vector integral. You have to specify the direction. Otherwise, you will get the opposite answer. All right, now let's see an example. Let's say we have, let's do a space curve. Okay. Say we have a curve. Let's say x equals t, y equals t squared, and z equals t cubed. It goes from origin to 1, 1, 1. So it means t equals 1, right? Let's find out the so-called work done by the force. And this force is given as a function of space. Let's say x, y, y, z, and zx. So what is the work done by a force? Well, it's just a physical name for the integral. And along this curve. And the curve has a direction from 0 to 1. Okay. So this is called the work. Okay. And then how do we do it? Remember, we do the inner product. So it's xy times x prime, and then yz times y prime plus zx times z prime, then integrate over time. Alright, so what is xy times x prime t is just 1, and yz times y prime is 2t, and zx times 3t squared, integrate from 0 to 1. Okay, but to actually do it, you have to replace x, y, z by function of t, because that's along the curve, right? So we see this is t times t squared plus t squared times t cubed times 2t plus t cubed times t times 3t squared. Alright, so what do you have? T cubed plus, this is 2t cubed, cubed to the 6, plus this is 3t to the 6. Right? Let me see if it's correct. Yeah, it looks correct. Yz times y prime, and so that's the integral. That would give you t cubed, then get t to the 4th over 4. Then this is 5, t to the cube, so it's 5 times t to the 7 over 7, 0 to 1, so it's 1/4 plus 5, 7. Then that's 28, and this is 7 plus 20, so 27. Alright, so that is a work. If I say the same curve but go backward, right, then what is the work? Well, then you can see it's f times dr with the backward c, right? So it's the same integral. Let's see, that is this one here. Three t 6 t, but t goes from 1 to 0, right? So it's going this way, the other way. Then of course that means it will be the negative. Okay. So that's what you do when you have a curve with opposite direction. Okay, now let's see a different example for the spatial vector integral. Suppose you have a circular path, and it's a circle, but we still need to say that the direction. It doesn't matter where you start. You can start from here and go around the entire circle, or you can start from here and go entire around the circle. It's equivalent, but you have to say what is the direction. This, let's call it counterclockwise. Is the default direction. We call this C, and if you go the other way around, clockwise, then it's usually we call it negative C, because that means it's the opposite of that C. So let's find out the integral of this C with the vector the vector field xy dot dr. Alright, integrate along that. Okay, how do we do that? Well, this is a circle, so let's use theta to parameterize it. So this is cosine theta and this is sine theta. Right? So theta goes from 0 to 2 pi, and then this will be x times x prime and y times y prime times d theta. And what is x? X is cosine theta, and cosine theta prime is negative sine theta, plus y is sine theta, and y prime is cosine theta. Ooh, do you see what happens? This and that cancels, so the answer is 0. So the integral is 0. Alright, and that is actually not so surprising, because this is a vector field that we showed last time. It's a gradient of this and it's a so-called gradient field, right? No, it's a gradient field, and turn out that if you integrate a gradient field over a closed contour, closed curve, you always get 0. Let's try the other one. Suppose you have the same circle, but sorry, this is not C. Just this integral is of that. And let's see what that is. Same circle. So this would be y times x prime minus x times y prime d theta. And what is that? Well, y equals sine theta, and x equals cosine theta, so it's a negative sine theta, and then you have a minus x equals cosine theta, y prime equals y is sine theta, so y prime is also cosine theta. And what is that? You have negative sine square minus cosine square, which is negative 1. And the answer is negative 2 pi. So it's a negative number. Let's see what does that represent. Let's plot this field, y negative x. when x equals 0, when y equals 0, x equals 1, you have a negative like that. Something like that. Okay, so if you trace it, you will see it's going along that. Right? So what does that mean if you integrate along the circle? Right? Along this circle. Well, you will see that this f is actually parallel. Oh, not parallel. Anti-parallel is 0. Sorry, it's less than 0, because this is f, right? And what is that? That's dr, because our circle is in the counterclockwise y direction. So f is always opposite to dr. So the dot product is negative. That's why you integrate over the entire circle, you get a negative result. So if you integrate over a clockwise circle, then you will get positive 2 pi. Okay, so we see that the integration along this enclosed circle is not 0. And actually, this is indication of that the vector field is not potential field, or you can say it's not a gradient field. But we'll prove it. Okay, we'll prove why it's the case. Let's see if we have anything else. I think that's enough for this section, and we will continue next time.